Pre-lecture video number 8, Limiting Reactants, How to Use Before and After Tables. One common method of finding limiting reactants focuses on looking at one single product as the determining factor for the limiting reactant. In this method, you assume first that one reactant is the limiting reactant, then you find the amount of a particular product you could make if all of that reactant is used up. Then, in a separate assumption, you assume the other reactant is limiting, then find the amount of that same product you could make if all of the other reactant is used up. In this way, you always compare the amount of the same product, and mole ratios take into account the coefficients from the balanced reaction. As an example, in the Haber-Bosch process, nitrogen gas and hydrogen gas react in a 1:3 ratio to form ammonia. If we start with 1 gram of each reactant, we can first assume nitrogen reacts completely. The grams of nitrogen can be converted to the moles of nitrogen by dividing by the molar mass. Then, the mole-to-mole ratio from the balanced reaction tells us that 2 moles of ammonia are formed for every 1 mole of nitrogen used up, telling us how many moles of ammonia that can be formed. Finally, using the molar mass of ammonia helps us find the number of grams of ammonia that could be formed. In a separate step, let's assume all of the hydrogen gas gets used up. Similarly, we can use the molar mass to find the number of moles of hydrogen used up, establish a mole ratio from the coefficients of the equation to find the moles of ammonia that could be created. Then we multiply by the molar mass of ammonia to find the number of grams of ammonia that could be formed. Comparing the amounts of ammonia, the smaller number is the maximum amount that can be produced and corresponds to the amount made if all of the limiting reactant is used up. This maximum amount of ammonia is called the theoretical yield, but unfortunately, this method does not tell us information about excess reactant amounts, which are sometimes useful to know. One way of tabulating data for stoichiometry problems is using a before and after table, which requires that you convert all of your measurements to moles of compound. The top row in the table corresponds to the amounts in moles of each reactant and product before the reaction begins. From the previous problem, we calculated the number of moles of nitrogen, the number of moles of hydrogen, and finally, since the reaction hasn't begun yet, there should be 0 moles of product. The second row is the change row, which tells us how much these quantities shift. Over the course of a reaction, the reactants decrease in quantity, and the products increase in quantity. If we abstract out this process, the amount of decrease corresponds to the coefficient multiplied by some unknown quantity x. So, for nitrogen, the change is minus 1x or minus x. For every x moles of nitrogen that disappear, 3x moles of hydrogen disappear, so we'd write minus 3x for the change in hydrogen. As we cross to the other side of the equation, the product should increase as the reaction goes on. So, for every x moles of nitrogen that disappear, 2x moles of ammonia will appear, so this is a positive quantity. Finally, if we add together the before and change rows, we get the after row as the sum of each column. We treat each column separately for these additions, so for hydrogen, we get 0.4960 minus 3x, and for ammonia, we get 2x total moles at the end of the reaction. This completes the table setup. Now that the table is set up, how do we find the limiting reactant? For the limiting reactant, the amount remaining after the reaction is complete must equal 0. So, one of the 2 reactant after cells must equal 0. Let's assume that hydrogen is the limiting reactant. Now we can set up an equation, 0.4960 minus 3x is equal to 0. We can then solve for x and check the other after cell to see if this works numerically. Since you cannot have negative amounts of a substance, if we plug in the value of x and receive a negative value, then you've picked the wrong limiting reactant. So, since hydrogen was not the limiting reactant, nitrogen must be limiting. Let's go through the equation again and set 0.03569 minus x equal to 0. We can again solve for x, then plug it into the after cell for hydrogen, and check to make sure that we have a positive amount of the excess reactant left over. This works out, so nitrogen is the limiting reactant, and hydrogen is the excess reactant, with 0.3889 moles of hydrogen left over after the nitrogen gets completely used up. Now that we are sure that we have the correct value of x, we can plug in x into the change line as negative x for nitrogen, as negative 3x for hydrogen, and as positive 2x for ammonia, then calculate the actual values for the number of moles left after the reaction for nitrogen, our limiting reactant, since there is none left, for hydrogen, which indicates the amount of excess hydrogen left after the reaction is complete, and the number of moles of ammonia created from the reaction, which is the theoretical yield. In this way, we can tabulate all of these amounts to represent all stages of a reaction and to more easily see the effects of having a limiting reactant.